तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we will continue our discussion on the Schottky barrier diodes, their IV characteristics, and we will go on with how close are they to the ideal characteristics. Okay. So, I have marked this as 1 because we will have at least 2 sessions on this topic, okay, because it is a detailed discussion on this. Before we get along on to that discussion, let us just take a look at some of the things we have already seen. We have shown that the Schottky barrier current density J can be expressed as J naught, just like the diode J naught into e to the power of V by V t minus 1. The only difference is that J naught comes up by a different mechanism compared to the p-n junction. We will have occasion to discuss today what is exactly the difference. Okay. What we have discussed here is that the current transport is through the transport of carriers over the barrier. Okay. All those electrons which have energy in excess of the barrier height will be able to give rise to current. So, through that approach we said that J naught will be given by this expression, and the whole thing here can put as a constant A star, because that depends on the material, because the effective mass comes there and the temperature. Okay. So, temperature is absorbed here and this A star is put there, which includes the M star, and of course, it depends upon the phi b n. As we have been telling again and again, if the phi b n is higher, this is smaller, it is better rectifying diode. If phi b n is smaller, it is a very leaky diode which is closer to the ohmic contact. So, here what we have seen is A star, you can, I am just pulling out this A star alone, and you can write it because all are constants except that Mn star is a material dependent quantity. It would vary from silicon, gallium arsenide, indium phosphide, etc. So, all other constants put together, it becomes Mn star by M naught. I have just discussed it last time, going through it quickly, so that we are focused on our discussion today. So, this thing is 120 into Mn star by M naught, amperes centimeter square per Kelvin square. So, now all that is required to evaluate J naught is this, evaluate A star and this phi b n and temperature. Take the case of gallium arsenide, evaluation of J naught for Schottky barrier on gallium arsenide, and we are talking of course N type substrate, okay, because those are the materials which are used for making FETs in gallium arsenide. So, A star is 120 Mn star by M naught. For gallium arsenide, this ratio is actually equal to 0.067, effective mass is very small. In fact, that is one of the reasons why the mobility is very high in the case of gallium arsenide. And then when you substitute for that here, you get A star is equal to 8.04, that is the Richardson constant. The A star is put to differentiate it from the A, usually we call it for area. So, not so that you do not confuse between area and this, it is put A star. Okay. And it also indicates you that star is related to the Mn star, effective mass. So, two stars related to each other. Okay. So, that is why A star and not related to area. Now, if the phi b n is barrier height is 0.85, which is usually the value that is obtained for gallium arsenide on N type substrate, okay, then you get at temperature T, J naught equal to that A star, which is 8.004 multiplied by T squared 300 degrees Kelvin square multiplied by e to the power of minus 5 B n by k T, 25 millivolts, 850 millielectron volts. All when you evaluate, it is about 10 to the power of minus 9 amperes per centimeter square. Okay, this is the range which we see in the case of gallium arsenide. You can see it is excellent in terms of the leakage current, etc. Take a look at silicon Schottky barrier. There the ratio is about 0.6 Mn star by M naught. So, therefore, the Richardson constant A star turns out to be 0.6 times 120, that is about 72 amperes per centimeter square per Kelvin square. Now, we have to, if you want to find out J naught, we do it at temperature 300. So, you have got 72 into 300 square into e to the power of minus 5 B n by k T. That 5 B n I have taken as 2/3 of E g, which is the value that you get when the Fermi level pinning is there. So, you get close to that point. Notice also that this particular band, this 5 B n is smaller than that of gallium arsenide. So, the moral of the story is you get higher 5 B n if the band gap is higher, because it is almost related to that E g. So, if you want to make Schottky barrier, you are better off with materials which have got higher band gap. Silicon, it is border case, because band gap is 1.1. If I want to make Schottky barrier with germanium, it is a hopeless situation. Okay. So, that is one very good point that one should note, that higher band gap materials are better suited for Schottky barrier. Therefore, you can imagine or you can extrapolate that it is better suited for making JFET or MESFET. For making MESFET, metal semiconductor FETs, you can make better with wider band gap semiconductor. That is what I wanted to point out here. So, now when you plug in those values here, you get 10 to the power minus 7 into 6, which is almost equal to 10 to the power minus 6. Now, you can see as compared to gallium arsenide Schottky barrier, which is 10 to the power minus 9, it is higher than that. So, it is leakage currents are more, reverse bias currents are more per centimeter square. Comparison of the IV characteristics of gallium arsenide and silicon Schottky diodes. Okay. Now, I am putting them down again here. J naught we just now estimated is 1.24 into 10 to the power minus 9 ampere per centimeter square. And if you use that J naught, you can find out what the voltage drop is using the IV characteristics. Just the clarification on what I have written there, what we use is J equals J naught e to the power of V by V t minus 1, that is the forward characteristics. What we are trying to find out is when this is 1 ampere per centimeter square, V is how much given that as J naught. Now, also you should note that okay, this is what we are trying to find out just by using this, and notice we can neglect very comfortably that term e to the power of 4. If you take even if 100 millivolts, 100 by 25 e to the power of 4 is large compared to 1. So, when you go to 200 millivolts etc., it is totally negligible. So, that we are just taking J is equal to is almost equal to J naught e to the power V by V t. We are using that to find out the voltage for 1 ampere. So, gallium arsenide we know that J naught is actually equal to 10 to the power minus 9 into 1.24. So, that number is substitute here, find V there. That is what we are trying to do when we have used this particular term here. So, J is equal to J naught e to the power V by V t. So, okay. So, V is equal to V t logarithm of that. So, substitute for all that 10 to the power minus 9, there is 1, this is 1.24 into 10 to the power minus 9. So, that goes up there. So, V is equal to 0.513 volts. This is actually not bad, it is slightly lower than what you get for the p-n junction diode is silicon, but getting closer to that of the p-n junction characteristics. Now, let us see what you get in the case of silicon Schottky barrier. J naught we have estimated it to be equal to 6 into 10 to the power minus 7. Okay. Now, same formula V is equal to V t logarithm of J by J naught. Substitute here 6 into 10 to the power minus 7, 7 has gone up there, 10 to the power 7 by 6, you get 0.358 volts. Now, you can see the problem that you see with the, or the differences between the silicon Schottky and gallium arsenide Schottky. The sum up all those results in the table, we have seen phi b n is 0.85. You have got higher band gap, so higher phi b n, because closer to 2/3. So, here 0.75. That makes the J naught smaller here compared to this silicon. Also A star, because of smaller effective mass 0.067 compared to 0.6 in silicon, this is 8 and this is 72. So, all these make the leakage current here is large compared to the J naught of gallium arsenide Schottky barrier. Now, when you use that we found out it is 0.513, there is no sanctity about 513 etc. You can say about 0.5, 0.54 that range, depending upon how much is the barrier height, that will vary. So, about 0.5, this is about 0.35 volts. Now, that is a forward drop for 1 ampere current, though this will go through all through the range of the current. So, if you see the IV characteristics now of the silicon Schottky barrier, this color, here we do not, so this color here, the silicon like that, gallium arsenide, smaller J naught, larger J naught this one, voltage drop is smaller in silicon compared to voltage drop in gallium arsenide. So, in other words, in the language of a circuit engineer, you can say the cut-in voltage of silicon Schottky is much smaller compared to cut-in voltage of a gallium arsenide Schottky barrier. The cut-in voltage of silicon Schottky is almost getting closer and closer to that of cut-in voltage of germanium p-n junction. Germanium p-n junction, all of us know that cut-in voltage is about 0.2 volts, okay, because of small band gap, barriers are small there. So, here the difference is mainly because of the barrier and the A star. That is what I just want to point out here. You have got IV characteristics approaching to that of p-n junction of silicon, that we will see now. So, let us see how to do the p-n junctions look. To recall what we already know about p-n junction, I take p plus n junction. Now, the total formula for this J naught of p-n junction diode is this. These are actually the carriers which are generated within one diffusion length on either side of depletion layer, diffusing into that. So, when you substitute, this is the minority carrier concentration in the n type region, thermal equilibrium. This is the minority carrier electron concentration in the p type region, thermal equilibrium. And you know that product of majority and minority carrier is equal to Ni square. Majority carrier concentration is equal to doping concentration. When you do that, Pn 0 is Ni squared divided by doping. Similarly, Np 0 is Ni squared divided by doping Na. That is all what we have done there. This is a very standard formula, let me not get into that, because we have discussed it in many forums. So, between these two terms, both will be almost comparable if the doping concentrations are same. But when you talk of P plus N diode, acceptor doping concentration is large compared to the donor doping concentration. So, this term in the denominator is much large, okay, this is very large compared to the doping on the ND. So, this term actually goes off, very small, 4 or 5 orders of magnitude larger here denominator. That means, this term will be 4 or 5 order of magnitude smaller compared to that. So, we could put that approximately QDP ND LP. Now, I just put this formula, so that you can substitute on that for yourself and see I have done that work for you. So, P plus N junction in silicon, I take doping of 10 to the power 16 centimeters cubed per centimeter cubed, lifetime, okay, lifetime of holes in N region about 3 microseconds, typical. This is only orders of magnitude to get an idea, I am putting these numbers. Do not say this is the number, this is a number, which will be varying depending upon the doping and the lifetime characteristics generally. So, dP is 12, that is okay for silicon, say, and Ni is 1.5 10 to the power 10 per centimeter cube at room temperature. So, we are calculating J naught at room temperature. So, now when J is 1 amperes for this case, this also has got J equal to J naught e to the power of V by V t, but J naught we are calculating using a different formula. Okay. So, this is V is equal to V t logarithm of J by J naught. J is 1 ampere, J naught is this quantity. So, that is why you get 10 to the power of 12 divided by 7.2. Okay. We are using the same formula, that is we are using the same formula, J is equal to J naught e to the power of V by V t. This J naught is something like about 10 to the power of minus 12 into 7.2. Okay. This is very small compared to this in the case of Schottky barrier. So, that is why for a given current 1 ampere you get larger voltage drop. In the case of Schottky barrier, silicon Schottky barrier, we got it as 0.35 or so volts. Here when you substitute for J naught and this 1, this is 1 and this is 7.2 into 10 to the power minus 12 ampere per centimeter square, you get a value of V which actually is much larger than that what you get for the Schottky barrier. Okay. So, what we have to see here is when you plug in those numbers, you get the voltage drop across the diode for 1 ampere per centimeter square is 0.64. So, you are used to here is number cut in voltage of silicon PN junction is about 0.6 or 0.65. That is the implication of that. Okay. About that current range you get that voltage drop. It does not mean that the diode starts conducting at 0.6, it conducts even better, even otherwise. If you go to 0.1 amperes per centimeter square, you get that voltage much smaller than that. It is conducting, but when you are using the red that particular range, you get 0.64. So, when you say cut in voltage, that is the meaning of that. If you actually expand the IV characteristics on the lower range, you get small voltage. Okay. So, do not be perturbed if somebody comes and tells I get a voltage, diode is conducting at 0.4 volts. It will, but a very low current density. That is the meaning of that. So, cut in voltage is a concept which is used by circuit engineers for convenience, because in the range of normal range of operation, that is the voltage across the diode. That is about 0.6 volts. That is the implication. So, people who are cautious will say 0.6 to 0.7. Okay, that is about the range. So, silicon Schottky barrier J naught is that, and we have 0.358 volts as the drop, that is the range. And what we say now is the voltage drop across the PN junction for a given current density is more than that of a Schottky barrier. That is finally the thing. So, that is what he said here. V for a given J, the voltage V across the PN junction is greater than the voltage across the Schottky barrier. Quickly go through the numbers for gallium arsenide. Schottky barrier we have seen it is about 10 to the power minus 9 into 1.29 and 0.513 volts voltage drop across the Schottky barrier. P plus N diode use the same formula that used for silicon, it is about that, very low, because femto and even lower than that ampere per centimeter square, because Ni is 10 to the power 6 as compared to 10 to the power 10 in the case of silicon. That low number makes it very, very small. Ni square is 6 orders of magnitude smaller. Okay. So, that is why it is so low, and when you use that for 1 ampere current density, same Vt logarithm of J by J naught if you use, you get about 1 volt. So, now the entire result is shown here in this table. Schottky barrier silicon, Schottky barrier gallium arsenide, we have seen it, 0.35 is the voltage drop, cut-in voltage about 0.3 and 0.5 cut-in voltage for gallium arsenide Schottky barrier. Go to silicon PN junction here. On silicon PN junction, P plus N junction, J naught is much smaller compared to the Schottky here, and then correspondingly voltage is, you can see 0.358 for Schottky barrier, 0.64 for PN junction. Gallium arsenide, okay, gallium arsenide PN junction voltage drop is about 1 volt compared to Schottky barrier of about 0.5 volts, lot of difference. Now, take a look at the total IV characteristics of all the things. I have put the Schottky barrier of silicon, I have put the Schottky barrier of gallium arsenide, I have also shown the p-n junction of silicon, p plus n junction, also p-n junction of gallium arsenide. So, moving from left hand side to right hand side, okay, the dotted lines are the junctions, the solid lines are the Schottky. So, on the forward conduction region here, you can say now minimum voltage drop 0.35 volts or 0.3 volts. I have put here as cut in voltage about 0.3, what I have put here is about cut in voltage, that is for silicon Schottky barrier. And for gallium arsenide Schottky barrier about 0.5 cut in voltage. Okay. And you can see here I put 0.65 for silicon p-n junction. So, all the curves extend to the right, and if you see the gallium arsenide p-n junction 1 volt. Now, just some information related to this. This property of higher cut-in voltage of gallium arsenide makes it useful for solar cells with higher open circuit voltage. When you shine light, if you take a junction, you will see there is a voltage developed. If the solar spectrum falls on the p-n junction, and if you just measure, put a multimeter there across that or a voltmeter, you will see there is a voltage developed. If you take silicon, you will get something like about, it will be less than that, less than the cut-in voltage, less than the built-in potential. So, it will be about 0.55, 0.6 if you get, you will hit the roof with joy. Okay. You do not get 0.6, after 0.55 volts it becomes tougher and tougher, whereas in gallium arsenide p-n junction solar cells you will get close to 1 volt, higher open circuit voltage. Okay. I will see if we have occasion to discuss this later on, much later, some aspects of these things. So, this is what I want to note, you to note. Also, you see the currents starting from this dotted line, higher voltage, lower J naught. This is the curve from here to here, and this one silicon junction, that dotted line is the second dotted line. So, here you move from this side to this side, and here you move from below like that. Smaller forward voltage, larger leakage, and if the leakage becomes largest, that is the ohmic contact. So, if this curve keeps on shifting towards the left side, this keeps moving down and you will have ohmic contact, close to the ohmic contact. So, you can see that silicon Schottky barrier is not so good at rectifying, it is not as good as gallium arsenide, it does the rectifying job, no doubt, okay, with a band gap of about 0.75 or so. You do get rectifying contact. So, it is not very encouraging like in case of gallium arsenide. Gallium arsenide almost see the characteristic close to the p-n junction of a silicon here also. Okay, now let us go further down. Benefits of Schottky barrier. In fact, I go before into that, few things I want to discuss. Okay, keeping this diagram in mind here, we will discuss one or two things. One thing is the application. The application of the Schottky barrier diode. Okay. Even in silicon technology, the Schottky barrier diode is used. It is not the proprietary of the gallium arsenide technology, Schottky barrier diode. You see that it is conducting at lower voltages, 0.3 volts. You can see if there is a junction in parallel with this, a diode and a Schottky barrier diode and a p-n junction in parallel, okay, this will be dominating. The current will pass through Schottky barrier diode. That property is made use of in fast switching TTL. Okay. Transistor logic circuits, if you see, you have the transistor, okay, in the TTL logic circuits, it is slow compared to emitter coupled logic ECL. The reason is, in the TTL the device goes into saturation, correct. I just go through that particular thing now. See, if I have just a simple example is, you show this inverter like this, I will put that plus there, okay, and pumping in current. I am not showing the biasing circuitry, etc. So, if you see, when I have the input actually going like this 0 to 1, what way it goes? In fact, IC versus VCE if you take, this just to recapitulate your memory on this particular switches when the bipolar transistor is used. So, I have the characteristics which goes like that with different IB. Okay. I have that characteristic. Now, you can draw a load line on that RL, which is the load line. So, you can draw that load line, okay, which so when the device goes from, when it is 0 here, it is off, and when it is 1, it is totally on. That is, you are driving base current with 0, that is here, you are moving on to that curve. That means, you are moving from here to that point. So, the transistor is driven from the cutoff to saturation. The transistor goes into saturation here. When the transistor goes into saturation, you know that there are charges stored in the region, base region, collector region, everywhere. So, if you want to come back from here to turn it off, okay, the charges stored in the transistor various regions will have to be removed. That is what makes it slower. You prevent the transistor, if you want to prevent the transistor to go into saturation, what is done in the TTL is, this I am showing one inverter only of the some portion of the TTL where some inverter comes in. You will have another resistor here, that is a different story, but I am showing finally the principle. I do not want this to go to this thing. So, what you do is, you prevent the transistor, when it goes into this portion, what are the status, what is the state of voltage across the emitter base and collector base. When the transistor goes into saturation, emitter base junction is forward biased, collector base junction also is forward biased. When it goes deep into saturation, collector base junction voltage will be almost equal to the 0.6 volts. If the junction is going to saturation, that is conducting, it will be somewhere here. Okay. Now, I do not want the transistor to go into deep saturation. When you say deep saturation, lot of the forward voltage across the transistor collector base junction is large, almost close to the emitter base junction voltage is 0.7. So, this may be 0.7, this may be 0.6, and it goes to that. Unless it is less, there won't be current flow. If both of them are equal, current will become 0. So, that never happens. So, what do? You put a Schottky barrier diode here. What they do in the technology is, I think I can put it like this. This is a Schottky barrier diode. Connect a Schottky barrier diode. In fact, you can actually integrate along with the transistor. Okay. Between the base and the collector, integrate a Schottky barrier diode, or you can put it separately. Make a diode, connect them within the surface, connect internally. Okay. The way they do it, I am not getting into the technology right now. So, they do it, this is done by putting a metal over the base region and the collector region. You make the Schottky with the N region collector, you put a metal on the N region, it becomes a Schottky barrier, and allow that metal to go over to the base region, okay, that becomes ohmic. So, you get a ohmic contact here, p type region, and the metal on the p type becomes ohmic, because low barrier height, because of the Fermi level pinning. Metal on the collector N region becomes rectifying very easily. So, without showing the diagram, you can feel that this single device with just a metal layer put between the collector and the base. Okay? So, that is the technology that is done there. This is the TTL, Schottky TTL, STTL. Okay. Here, what happens when this goes into this region here, when the device goes into the saturation, this voltage across that will never become 0.6. Why? There is a diode connected across that Schottky barrier, which will divert all the current instead of going through that, it will divert through that with a smaller voltage. So, okay, there is certain current flowing through that. That current will flow through this device. So, the current instead of going through this, it will go through that. So, that voltage drop across that is limited by the voltage drop across the device. So, now you can see this diagram. Instead of 0.6 volts here, PN junction across when it goes into saturation, you have put a Schottky here, this one, this dotted and this one, first one. That voltage drop across that is 0.3 volts. So, the voltage drop across the collector base junction, which is forward biased, is now 0.3 volts. So, it has not gone so much into deep saturation. Okay. Now, when a diode and a junction is forward biased, you have got carrier concentration raised as e to the power of V by V t. When a forward biased junction is there, carrier concentration is raised as e to the power of V by V t. Now, V is the forward bias. You have reduced that V from 0.6 to 0.3. So, e to the power of 600 by V 25, that is the V by V t. So, this is 600 by 25 originally, carrier concentration. Okay. If you just recall, I just write that thing here below. See, if I take the n region, P n boundary condition is P n 0 e to the power of V by V t. This is the charge which is injected into the n region when a forward bias collector base junction is there. So, if V by V t, if V is 600, this is 600 by 25, this is about 24, e to the power 24. Okay, that may be something 10 to the power 14 or of that order, very high. So, instead of e to the power 24 now, by connecting this, what you have done is that you have reduced to e to the power 300 by 25, that is 12. A factor of e to the 10 to the power 12, huge reduction in stored charge, the speed up is tremendous. That is how you get the speed up in this Schottky barrier diodes. So, Schottky barrier diode is a very important device for high speed circuits. Okay, that is falling with the theme of our discussions in these high speed circuits. Okay, so, high speed devices are made in silicon with Schottky barrier connected across the collector base junction, integrated with that. Okay. Maybe later on we may have time to recall, but this is the key to the thing. That is one point. Number 2 that I want to discuss is why that difference between J naught between the PN junction and the metal semiconductor contact. You do not see this explicitly discussed, okay, but you see very closely examine the mechanism of current transport, you can easily figure out what is happening. Okay. If you take metal semiconductor contact, how is the current transport taking place? You just take a look at that. You take a look at how the current transport is taking place in the case of P plus N junction. What is the difference if you see? You will see why the J naught is smaller in PN junction compared to, or why the currents for a given voltage. See, for a given voltage or for a given current, the voltage is larger in the PN junction compared to the metal semiconductor contact, or put it other way, for a given voltage current is smaller in PN junction. Why? We will take a look at that now. This is a very important concept that one should see actually. Let us draw the device, the energy band diagram which we have been drawing. Okay. That is the for Schottky, and we draw the Fermi level there, EC, EF, EV. Okay. You recall that we had drawn this sort of diagram. In fact, it is a very powerful diagram to visualize what is happening. Those are the electrons which have energy above that, which are able to cross. That is the one which gives rise to J naught. This is the phi Bn, metal semiconductor. Okay. This is the metal or Schottky barrier. People like to call this more as Schottky barrier than the metal semiconductor. I just called it because when you say metal semiconductor, it can be Schottky barrier, rectifier or ohmic, general term. Now, this is thermal equilibrium. When you forward bias, okay, here you have got similar distribution here. I am redrawing the diagram which you have been drawing, and this is balanced by that. These electrons have energy more than this barrier, these electrons have more than the barrier, that is balancing. When I forward bias, this is forward bias. Okay. This is forward bias situation, the conduction band. Valence band also will go up similarly, okay, by the same amount equal to V, forward bias voltage. Now, this distribution goes up, and you have many more electrons which are able to cross. So, what we have done, I am just discussing this deliberately because to see what is the difference between the p-n junction and this. These extra electrons have energy above this. Okay. We have computed this, what is the electron concentration there. If you remember how we computed, you computed q n whatever electrons are there above that, okay, because they are the electrons which are actually here impinging on the boundary into the mean velocity. That is all what we have done, current density. Now, in the p-n junction also same thing happens, absolutely no difference. The difference is what happens beyond this point. Let us take a look at what happens beyond this point. These electrons, whatever have energy above that, of course, there are some part of it is compensated by this. Let me talk of only the total quantity now. They are impinging, reaching here, they are here. We called it Ns equal to n and 0 e to the power v by V t. All those numbers are able to cross the barrier. Now, how much is the current depends upon what is the fate of these carriers after they cross the barrier. What is the number that are reaching that metal? How much is the number compared to the total number available in the metal? That is the key to the whole thing. In the case of Schottky barrier, in the metal you have got 10 to the power 22, 23 of that order number of electrons per centimeter cubed. What number of electrons which are crossing this barrier here, how much are they? If this is 10 to the power 16, much smaller quantity compared to that. Okay. N n 0 e to the power minus v by v t, n n 0 e to the power minus v by v t. So, that quantity, in fact, minus v b I minus v, if you look back, it is related exponentially to the voltage. Okay. So, you have actually that number much smaller than equilibrium concentration. So, if you have 10 to the power 16 as the equilibrium concentration, the crossing number is much smaller, maybe 10 to the 11, 10 to the 10. So, it is like putting a drop of water into the ocean, it disappears immediately. In the sense, it is not disturbing its thermal equilibrium here. When the carrier concentration is so large, from here to the contact, okay, if I just can draw, I will remove this here. Okay. If I have a metal like this and a semiconductor, I am applying voltage V, this is n type. What we are talking of is these electrons which are crossing here. Okay. Now, you have got small, even the smallest field that is appearing there will be able to take away those electrons, because the total electron concentration is very large, 10 to the power 22 if you have. Even a very small field will help to remove those charges which are injected to give rise to the current. It is again here you calculate it as J n into V. J is equal to Q n of S into V x. That is when it is here. When it goes into metal, what is the current? Same current should flow if all of them are flowing out. That okay, this is across the barrier. In the metal, J will be what? Q into N in the metal plus whatever Ns is injected, that is negligible. So, let me rewrite that. In the metal, J is equal to Q N in the metal plus N of S, which has been injected there, into velocity in the metal. So, this is actually this is small compared to that. N of M is very large compared to N of S, which would mean, just watch me carefully, this is very large compared to that. This is the mean thermal velocity, whole thing is given by transported because of its higher velocity, but this is orders of magnitude larger than that. What will be that quantity? This current quantity is there. So, whole thing limitation comes up how much can go across the thing. So, all of them will be transported with very low velocity. Here, very low velocity means mu is equal, V is equal to mu in T. Okay. So, there is mobility of electrons is there in the metal. So, V can be very small, that means very small electric field will take away, give rise to this current in the metal. Very small electric field in the metal will be able to handle this amount of charges which are injected to remove them away, because it is not this that is flowing through that. Because the moment there is a voltage across the metal, the current transport is due to not merely due to that, it is due to the whole of the things. Because okay, you are not dealing with that injected electron alone when you apply voltage. Total number is what was existing originally. So, that is possible with very low velocity, which would mean that is possible with very low field there. That means very small millivolts drop across this will be enabling to allow the current flow. So, what I am trying to point out is, in a Schottky barrier diode, the current transport, the extent of current that is flowing through the junction is totally controlled by that component, because this component is not limiting it, because with very small field that is able to take away all the current, because Nm is very large there, metal. Is okay? So, that is the thing. Nm electron concentration in the metal is very large compared to the electron concentration on the surface of the semiconductor. Nm is the electron concentration in the metal, that is the one which is very large. Therefore, this is not limiting that, they are just swept away whatever is injected. So, total current is limited by this. Okay? That is the way we have estimated the current. Now, in the case of p-n junction also, what happens, let us see. I think what I will do is, I will just retain this here, I will go to the on this side p-n junction, I will say p plus n junction. Okay. I will switch over from there, I will retain that there in case we want that for discussion. We will focus here now. In the case of the p-n junction, what is the diagram? I will take p plus n. Now, you can, the story is totally different. Okay. What is the energy band diagram? You take a look at this in the same light as the Schottky barrier diode. EF, thermal equilibrium, okay, and this is p type material. I will put that as the junction, okay, and you will have depletion layer there. So, from there onwards, due to the built in potential, and here that is easy. P type material, N type. I have not shown the Fermi level very not too much difference, but if that is P plus, it will be closer to that P n junction. Or even if you do not put P plus, it is okay. Our discussion holds good for that. What will be the distribution here? Exactly same diagram that we drew for metal semiconductor junction you can put. This goes like that. That is the electron distribution. When the Fermi level is equalized, what has happened is now these have some energy. This is the barrier. What you see in the case of Schottky barrier, that same type of barrier is there for electrons. And here, what is electron concentration? Very small. So, this is actually like this. Now, look at the fate of the electrons which are injected from here to here when a forward bias. When a forward bias, that dotted line, this becomes like that. I can actually compute the total number of electrons which have energy to cross this, exactly the way you have computed the electron concentration at the surface here. You can compute what is the electron concentration on the surface, N 0 e to the power of V b I minus V by V t, Q of course, V t, V b I minus V by V t. That is the concentration here. That is what you are doing is you are computing how many have got that energy above that. Now, all of them are capable of crossing this barrier, that extra. Previously, this was equal to that thermal equilibrium. When you forward bias, this, okay, sorry, let me put it this way. When you forward bias V, when you do the forward biasing, this whole thing gets lifted up, more of the carriers are there. So, if you give a chance to those electrons to be removed away once it is injected to the P region, the same way that is done in the case of the metal, the current will be equal to that, exactly that. Supposing this barrier height is the same as that pi b n that you got in the Schottky barrier, you would have got the same current. But if this barrier height, which is a built in potential, is the same 0.75 volts, the current that you will get will be much smaller than that for same voltage, because reason is these electrons which are impinging on the surface with the same equation q n s, n s is actually this quantity q n s into V of x. Okay. They are striking the surface, they are able to cross the barrier, but having crossed the barrier, they find that they are minority there. Okay. Once they are minority, it is actually now how much is the current depends upon which of them is larger. In the case of Schottky barrier, you are impinging, the current is transported across the barrier with q n s into V of x, and from that point onwards there is no limiting because carrier concentrations are very large, q n into V, q n m into V. So, very small V or very small drift field will take away those electrons, whereas here n is minority carrier. This may be what you have here, the electron concentration here may be 10 to the power 10 or 10 to the power 11, what you have here will be 10 to the power 2, 10 to the power 3. So, now what happens is, if you want to remove them at the same rate, you must have a large velocity. For large velocity, there should be a field coming up. Okay. Alternately, what happens is, the carriers are not removed as fast as you require, because there is no field available there. So, they get piled up here. The minority electrons which are injected here get piled up here. Now, you take a look at the if you see the boundary condition here, P p 0 is the whole concentration, I am sorry, this is the PP 0 and N 0 is the electron concentration there. You are pumping in electrons at a very fast rate here, governed by that equation Ns into Vfx. So, but it is not able to take it away because there is no field there. Okay. So, immediately when you inject at a fast rate, what happens? You are dumping electrons at a fast rate from the boundary. So, therefore, that concentration goes up there and there is no concentration there. So, from that point onwards it is carried away by very familiar sight now. The concentration builds up there because it is not being taken away fast. It is not being taken away fast because it is minority carrier and it would need very large field to take it away. There is no field there, large field. Small fields are not sufficient. So, carriers get piled up there, that is why this builds up here. This is a slightly different concept that you usually see, but the fact is that. So, you will have here okay, I am sorry, this I think you put it as NP, correct? Whole concentration P type material, whole electron concentration P type material, and then you have got NP 0, that goes up. So, what is the mechanism by which the current is transported now through that P layer? By diffusion. Because of this concentration gradient, the transport, once it crosses the barrier, the transport is by diffusion, and the diffusion is actually slow process. So, this is slow compared to the transport from here to here. The equilibrium is hit, so that the rate at which is removed controls the total current. So, the difference in the Schottky barrier and the metal semiconductor contact for a given voltage in the Schottky barrier, the current is controlled by the rate at which you are able to transport across the barrier, because from there it is taken away fast, because large number of electrons are available in the metal. In the case of p-n junction, the current is controlled by the rate at which you are taking it away from that. One is the rate at which it is coming here, other one is the rate at which it is taken away. The current is controlled by a slower process, whichever is slow is controlling. In the p-n junction, this process is slow, diffusion, driving force is the concentration gradient. This process is faster. So, this is the one. Two of them in series, the slower one controls the current flow, slower one is the diffusion, and that magnitude is much smaller than what is crossing there. So, this is smaller compared to what is crossing there, and this is the total current, which is actually given by Q d n Np 0 by Lp, whereas that current would have been, if you have been able to take it away completely, that will be that A star T square e to the power 5 p n by V t, whereas this turns out to be Q d n P n 0 Np 0 e to the power V e to the power V by V t. So, this is small. So, going back to sum up what I said about these two currents now, okay, you take a look at this particular thing. This portion is able to carry the current fast. So, total current is controlled by how much is coming through this, okay, which is much larger compared to what is being taken away here. This is very small compared to, okay. In both the cases, the rate at which it comes up here for the same barrier height will be same, but the mechanism by which it is taken away in the other region, that controls. Here it is taken away by drift in the presence of large quantities of electrons, that is why it is fast, okay. And in the other case, it is taken away by diffusion, and notice you have got this charge storage effect. This is the charge that is stored here. Similarly, on the other side, you can talk of whatever holes, then same thing you can talk of. Holes are hitting the surface at fast rate, but they are taken away by small rate, because hole concentration in the n region is very small. Okay. So, these are the two subtle differences between the two, and for a given voltage, the current there is smaller, because current is ultimately decided by diffusion. That is the reason why physically this current in the p-n junction is smaller compared to this current which would have gone up all the way up there. Okay. Or for a given current, you can drive a particular current with a smaller voltage with Schottky barrier compared to that. That is actually the key thing for that. Okay. So, in fact, I just went round going through this, because this particular point is not clear. This whole thing becomes clear only when you look at it this way. The electrons having distributed there, how many electrons can cross that, and once they are injected beyond that point, what happens. So, I think that is about the main thing that I wanted to point out to you. So, one of them is the Schottky barrier used in TTL because lower voltage, other one is a mechanism. So, also I have pointed out to you today that the charge storage here is there because minority carriers are stored. What about charge storage here? Absolutely no charge stored, because it is very, whatever injected is very small. No charge storage effect here, either here or here. So, whenever there is no charge storage effect is absent, whenever charge storage effect is absent, you can say the device is faster. So, in high speed circuits, it will become very effective to use a device which has no charge storage, that is the Schottky barrier diode. Okay. In p-n junction, always you will have charge storage effect, and that will be slower than the Schottky barrier. So, you will see in the logic circuits with gallium arsenide, you will use Schottky barrier diodes. With that, I will conclude the discussion today. We will continue on some aspects of this in the next lecture.